The safest way to build a nuclear reactor is actually over a tank of water. Owing to the weight of the containment, the reactor itself, the foundation, and the raft that would be necessary, the tank of water might have to be 300 to 400 feet across and 400 feet deep. In the event of a serious casualty to the reactor, seacocks would be opened on the rafts, which would open air outlets in and cause the raft to flood and sink. So the reactor and the raft would sink to the bottom of the tank. That entire volume of water would then be used to keep the reactor cool to prevent it from melting. It would be best, of course, the control rods for the reactor would be inserted before the entire thing sinks. Owing to the fact that it is floating, the reactor is actually isolated from earthquake waves known as S or shear waves, which move objects from side to side. The water prevents that stresses from being transferred to the reactor. This protects the reactor. The other type of major earthquake motion, which is called a pressure wave, which bounces buildings up and down, would also be reduced because the reactor and the raft are floating. This reduces earthquake stresses, which makes it easier to build the reactor. The cost of building and excavating that enormous tank of water should be less than $1 billion. When a reactor costs $8 to $10 billion, that's not a lot of money, and it might even save money from reducing the needs for earthquake protection. The connection of the piping from the reactor at the raft to other facilities, such as the turbine complex, needs to be worked through. The pipe needs to be a little bit flexible to allow for some movement, but has to be secure enough that there is no leakage of pressure. In the event of a casualty, there has to be some kind of clamp that can be released that joins the pipe on the raft and the reactor to the pipe on the ground itself. This allows the reactor to sink. The best design of reactor for this is probably what's called a pressurized water reactor. A pressurized water reactor has one circuit of water that moves through the reactor and then goes to a heat exchanger. The heat exchanger then heats up water, which powers the turbines. The other form of reactor, the water is actually boiled in the reactor and goes directly to the turbines. When those pipes are separated, there's a greater release of radiation. Because of the two circuits of a pressurized water reactor, the water around the reactor, which is the most radioactive, is still contained while it sinks and is not released. Inside the pressure vessel itself, there would need to be an inlet pipe to allow it to flood on the inside, and an outlet pipe near the top of the dome that would allow the current air to escape and water to replace it. At the top of the dome, it would probably be a good idea to leave a small amount of airspace to allow for water expanding. When the reactor has been sunk, the water would flow in at the bottom, be warmed by the heat from the reactor, rise because it is lighter, go through the pipe at the top of the dome, and then flow out through a pipe, the outlet of which would be higher than the top of the dome. This would then cause passive circulation, allowing the water to constantly flow and to keep the reactor cool and to prevent it from melting. The reactor, of course, would be lost at this point. If a boiling water reactor were to be used, there would be some release of steam, which would be somewhat radioactive, principally with something called tritium, which is a form of hydrogen. It is a relatively short-term amount of radiation. It decays relatively quickly, and it is better to have that released than to have the core of the reactor melt. But again, a pressurized water reactor would have the minimum amount of radiation leakage. Where the raft and the ground come together would be covered with perhaps a semicircular or elliptical covering made of metal or other material to protect the water, prevent it from being contaminating with debris, and also prevent it from freezing in winter. Although some of the heat from the reactor could also be used, again, to prevent the water from freezing in winter.